morning, everyone. Today we will continue about our last topics, the chops, cold heavy oil, production with sand. Today's topic we will start at part 5, because the part 1st to part 4th we have already told. So before we talk about this part, I will show a brief introduction video of oil sand in Canada.
Alberta's oil sands. It's the world's third largest oil reserve, 161 billion barrels of recoverable oil in the ground. They're a huge part of Canada's economy, contributing trillions to Canada's GDP over the past 50 years, generating billions annually in government taxes, revenues, and royalties, supporting small and medium-sized businesses from coast to coast, and attracting hundreds of thousands of workers from every part of the country. But how much do you know about the oil sands? Alberta's oil sands are contained within the Western Canadian Sedimentary Basin, which formed from the decomposition of plants and marine life about 200 million years ago, when Western Canada was believed to be mostly underwater. Microbacteria contained within the oxygenated water fed off the lighter hydrocarbon molecules, leaving behind a heavy, complex hydrocarbon known as bitumen. There are an estimated 1.8 trillion barrels of oil in the oil sands, but only 10% of those barrels can be economically recovered with current technology. That works out to 161 billion barrels of recoverable oil in the ground. To put those numbers into context, the industry currently extracts about 1 billion barrels a year, accounting for 2/3 of Canada's total oil production. Oil sands are a loose, unconsolidated mixture of sand, clays, and water saturated with bitumen. Oil sands are mostly coarse silica sand, about 80%. Fine solids and clays make up 5%, water is another 5%, while bitumen saturation rates average about 10%. Bitumen is a hydrocarbon compound with a very long and very complex molecular structure. Bitumen is high in carbon, low in hydrogen, and contains a relatively high amount of sulfur and heavy metals, especially nickel and vanadium. Bitumen is an extra heavy oil and contains as much as 20% asphaltenes, which are complex hydrocarbon compounds with a very high molecular weight. Asphaltenes are what make bitumen thick, viscous, and almost solid at room temperatures, giving bitumen that smell of tar or asphalt. While all crudes contain asphaltenes, bitumen has more asphaltenes than conventional oil and even more than heavy conventional oil. To make oil from the oil sands, first you extract the bitumen from the sand, then you either upgrade or dilute that bitumen into a marketable crude product, which can then be shipped to a refinery for final processing. There are two ways to extract bitumen from the oil sands, either by pumping steam into the ground, which is referred to as in situ extraction, or through surface mining. The method used depends on the depth of the deposit. For deposits located deep underground, steam is pumped into a well which extends deep into the reservoir. This steam heats up the reservoir, reducing the viscosity of the bitumen, allowing it to be pumped up to the surface. This mixture of bitumen and condensed steam is then sent to a processing plant, where the water is separated from the bitumen, cleaned up, and sent back to the steam plant, leaving behind a very clean bitumen product. There are two types of in situ technologies: the original cyclic steam stimulation facilities, which use a single well for both steaming and bitumen production, and the more common steam-assisted gravity drainage facilities, which use separate wells for steam injection and bitumen production. Both produce a clean, marketable bitumen, which is diluted and sold to market as a heavy oil blend. About 20% of Alberta's oil sands are too close to the surface to be extracted in situ. In this case, traditional mining technology is used to recover the bitumen. The mined oil sands is trucked to a processing plant using very large haul trucks. The deposit is loosely crushed and then conveyed to a bitumen production facility where it's mixed with hot water, producing a pumpable slurry. Coarse sand is gravity separated from the bitumen and sent to a temporary tailings storage pond where the water can be recovered back to the process plant. Bitumen froth from extraction, which still contains a lot of water and fine solids, is then mixed with a light hydrocarbon, which reduces the viscosity of the bitumen, liberating most of the remaining fines and water, leaving behind a relatively clean bitumen product. There are two types of mining facilities, distinguished by the type of hydrocarbon used to clean the bitumen froth: the original naphthenic facilities and the newer paraffinic facilities. NFT bitumen has way too much water and solids to be pipelined very far, so that bitumen goes to a nearby upgrader. However, PFT bitumen is very clean, so it's typically diluted with condensate and sold directly to a refinery without being upgraded. Since bitumen from a traditional NFT mining facility has too much water and solids, it can't be diluted to meet pipeline specifications, so it can't be shipped very far. This bitumen therefore has to get processed in an upgrader, which is usually located very close to the mine site. Aside from removing the solids, water, and hydrocarbon used in froth treatment, upgraders convert the bitumen residue, which is the sludge left behind after crude distillation. Unlike the gas-oil fractions, which are used to make gasoline and diesel, residue doesn't evaporate very easily and will produce a lot of lower-value asphalt at the refinery. And since bitumen is an extra heavy oil, it will produce a lot more sludge, even more than conventional heavy oil. Upgraders basically upgrade or convert this residue into higher-value gas oils using equipment like crackers, cokers, and hydroconversion units, which basically break up the long-chain hydrocarbon bonds and improve the hydrogen-to-carbon ratio, either by removing carbon or adding hydrogen. This converts the low-value residue into higher-value naphtha and gas oils. The last step in the upgrading process is to take all of these streams and remove contaminants that were originally contained in the bitumen, such as sulfur and nitrogen. After this cleaning step, each stream is recombined into a final crude oil product known as synthetic crude, which is a very clean, residue-free, light, sweet crude. So just to recap, there are almost 30 in-situ facilities and 2 PFT mining facilities that produce 2 million barrels per day of marketable bitumen, which is diluted and sold as a dilbit blend, and 4 mining facilities which send their bitumen to 4 upgraders, which produce about 1 million barrels per day of synthetic crude. That all works out to about 3.5 million barrels per day of crude, which is sold to refineries, including the diluent portion. Starting with the 1 million barrels of light synthetic crude, about half gets used in Canada, mostly Alberta, and the other half gets exported to the US, mostly the Midwest, with smaller volumes going to Washington state. As for the 2.5 million barrels of dilbit that come from the oil sands, only a smidge goes to Canada. The bulk of it goes to the US, and a large portion of that, more than 2/3, ends up in the Midwest region because, well, that's just where the pipelines go. Well, Canada has a lot of upgraders which are basically partial refineries. So Canadian refineries are better suited for synthetic crude, which has already been partially refined. So that's why very little bitumen is processed in Canada. To process bitumen, you need a very complex refinery, basically a refinery with a built-in upgrader, just like the ones found in the US. Western Canada has 6 crude export pipelines, all originating from Alberta: Trans Mountain, which runs to the west coast; Rangeland, Milk River, and Express, which run south to the Rocky Mountains region and connect to the Midwest; Keystone, which connects to the Gulf Coast via the Midwest; and Mainline, which runs to the Midwest and also connects to the Gulf Coast. Well, let's look at the math. Excluding space for products, the 6 pipelines have a total capacity of about 4 million barrels per day of crude. Western Canada makes 4.8 million barrels, including diluent and conventional oil volumes, and regional refining capacity is about 600,000 barrels per day. So that leaves 4.2 million barrels per day to be shipped out to other customers. So yeah, Canada is a bit short, at least until the Trans Mountain expansion comes online in 2023. Alberta makes a lot of dilbit, over 3.5 million barrels per day, but local demand is very low, like 90,000 barrels. So all that excess has to be exported, and when the pipelines are full, producers have to either store their oil or ship the extra barrels on rail cars, and that all adds to the cost of shipping that oil to the customer, which drops the oil price in Alberta. Yes, there are many different oil prices depending on grade and demand for that particular grade at a particular location. In Alberta, for example, the heavy oil discount averaged $13 a barrel in 2021, whereas in Houston that differential was only $5. That's because there's very little heavy oil demand in Alberta and lots of supply, but heavy oil is very scarce in the Gulf Coast, while refinery demand for heavy oil is very, very high. If you're looking at the same grade, WCS for example, then the price differentials reflect the cost of shipping that marginal barrel to the final customer. So for WCS, that would basically be the cost of shipping that crude by pipeline, assuming no other constraints in the system. In 2019, the oil sands emitted 84 megatons of CO2 equivalent. That worked out to about 15% of Canada's total emissions. Those emissions are split about half from in situ operators and the other half from mining and bitumen upgrading. Most of those emissions are from the burning of natural gas for steam and power production, especially for in situ operators. Diesel-powered haul trucks and tailings ponds are a big source for mine operators, while upgraders burn fuel to heat the bitumen feedstock to high temperatures. From extraction to the point of combustion, the average US barrel emits about 500 kilos of CO2 equivalent per barrel. Remember that extraction methods are only a small part of total emissions. Most of the carbon contained in a barrel of oil are released at the point of combustion. So the average barrel refined in the US is actually on par with mature SAGD facilities like Cenovus's Christina Lake and non-upgraded oil sands mines like Imperial's Curl Mine. Aside from improvements in efficiencies and technology advancements, getting to zero emissions will likely come through carbon capture and storage. All of the major oil sands producers have committed to being net zero by 2050 in support of the federal government's mandate. Wow, that was a very quick 10-minute run through Alberta's oil sands industry. Hi, my name is Anna. I'm the editor of Oil Sands Magazine. If you're looking for something more detailed, I would invite you to check out our 101 short course, which is in a similar format but a much slower pace. The course runs for about 2 hours and includes a downloadable PDF technical guide and a transcript of the videos with links to references and further reading material. And for a deeper dive into any of these topics, you can always check out the technical library on our website, which is totally free. I'll leave the links below. Thanks for watching. Bye for now.
Con Fulltigo tienes lo que quieres. Lleva un plan postpago más internet, hogar y Max incluido por un año por
Okay. Let's start the part 5. Case histories. Luseland Field. Horizontal wells. 5.1 Luseland Field history and reservoir parameters. The Luseland Field in Saskatchewan is a particularly important case history for a number of reasons. It has been on production continuously since 1982. Since 1984, there have always been approximately 30 vertical wells on production, allowing direct gross average field production comparison over time. Wells were drilled on 40-acre spacing, and there has been no infill drilling in this field during the study period. The company that operated the field installed and tested a group of 6 horizontal wells in the same field during the period 1992 to 1994. Old vertical wells were converted to channels production during the years from 1992 to 1993. Recompletions with larger diameter perforations and conversions to higher capacity PC pump were undertaken on select wells during 1994 to 1997. Thus, the Luseland field allows a direct and unbiased comparison of field performance under three different conditions: horizontal wells in three different areas of the field, vertical wells with minimal sand production, and production from the identical vertical wells, but with the deliberate encouragement of sand influx troughs. The basic properties and parameters of the Luseland field are present in Table 5.1, along with a comparison to a west-central portion of the heavy oil belt in Venezuela. The Table 5.1 Luseland and Figa properties. This is the left line is the parameters. The depth is 730 meters and 400 to 800 meters. And the pressure is 6.3 MPa. Another field is 3.8 to 8 MPa. And this one hydraulicity is 86%, and the other field is above 90 to 95%. The bubble point, the Luseland is 95%, and the other oil field is above 90%. And temperature is the bottom hole temperature is Luseland is 30 degree, and the other oil field is 44 to 60 degree, and the porosity in Luseland is about 30%, and the other is 29 to 31%. Permeability in Luseland is 2 to 4 D, and the others is 1 to 15 D. And thickness in Luseland is 5 to 15 meters, and the other oil field is 6 to 40 meters. Viscosity in Luseland is 1,400 cp, and the others is 500 to 600 cp. The dead oil viscosity in Luseland is 12,000 to 30,000 cp. The others they don't have the number. The API in Luseland is 11 to 13.4 API, and the others is 8 to 11 API. The solution gas type in Luseland is above 90%, and the others is also above 19%. Yeah, that's all. For the Venezuelan case, parameters values have been given a range for the shallower reservoirs in the southern part of Zueta province. The loose-land parameters are quite typical of heavy oil in Canada, except for one atom. SW is more typically in the range 0.12 to 0.16 rather than the 0.28 value present. Uh, 5.2 Production history for Luseland field. Figure 5.1 is the plot of the monthly oil and water rates produced from Luseland field from its inception to December 1998. Four distinct phases are defined. Phase 1 is the 10-year initial period. The wells were completed with conventional, widely spaced, small diameter perforation opening, probably or 13 shots per meter, with 10 to 12 millimeter openings. Reciprocating pumps were used to achieve a production rate of 20 to 30 barrels per day of oil. Although a few wells had PC pumps installed in the late 1980s, apparently the wells were not perforated at this time, and the PC pump were not highly successful. During this phase, small amounts of sand entered the well, probably 0.25% to 2% by volume of produced liquid in each well. Thus, chops processes were occurring, but limited by the rate at which the well could be produced and by the size of the perforation parts. Careful examination of the data shows that the wells were slowly becoming more productive with time. This can be partly ascribed to the increase in rate and develops as a more permeable zone grows around each chop's well. Phase 2 involved drilling and producing a set of 6 horizontal wells with slotted liners or open-hole completions. These 6 500 meters long wells was drilled in 3 different geographical regions in the same area, but one of them was placed centrally in the best area of the field, near where the 3 original vertical wells were produced. Table 2 contains the production history for 5 of the 6 horizontal wells. The 6 never produced oil. Table 5.2. This table shows us the 6 wells, different wells. We can see the average oil production from 5 to 227. Yeah. The result, someone is good. Yeah, the 2, 3, 4, 5. This 4 wells is good, but the first well is not good. Clearly, the phase 2 horizontal wells were failures. Figure 5.2 shows the production history of the most productive one, the wire 29, that produced just over 68,000 bottles. Phase 3 is the chops phase for the Ruslan field, starting in late 1993. A change in philosophy took place, and over a number of years, the original 30 vertical wells were gradually recompleted to aggressively produce the sand. This involved reperforating the interval using large diameter entry ports, 20 to 22, and more closely spaced, charged 26 per meter, so that larger volumes of sand and oil could enter the wellbore, unimpeded by perforation restrictions. Re- Reciprocating pumps were replaced by PC pumps, with the base of the pumps seated about 1 meter below the lowermost perforation port. Operation of the PC pumps was gradually optimized over a period of many months to several years for each well. PC pump efficiency in chops wells is generally optimal when the fluid level in the annuals is maintained low, yet not so low as to allow gas to enter the pump. This applies the maximum drawdown to the formation without risk of burning the pump, which can happen rapidly if the well is operated without fluid. Over time, individual well production was adjusted so that fewer than 10 joints of fluid, less than 100 meters, were maintained in the annuals. Larger capacity PC pumps were installed in several of the best chops wells in the period 1996 to 1997, and this further boosted oil production rates in the field. In 5 wells in 1997, tubing size was increased to 4.5 inch, 112-meter diameter, so that a higher tonnage could be used in wells without backing off the tubing or impairing it through excessive tonnage. By 1997 to 1998, well conversions and optimization had resulted in an increase in the overall oil production rate by a factor of about 4 to 5 compared to the period 1982 to 1992. On an individual well basis, per 1993 production was about 4.5 meters per well. After 1997, it was 21.6 barrels per day. A series of typical well histories is presented in Figure 5.3, 5.4, and 5.5. Phase 4 started recently in the middle 1990s. This phase has involved drilling additional settled wells off the center of the structure, and this drilling program has had mixed results. Some of the wells are good chops producers, but some of the wells will rapidly become poor oil producers and good water producers. It is believed that the new flank wells are producing large amounts of water early in their life because of proximity to the laterally offset zone of more bottom water below the region oil-water contacts that are closer to the thinner flanks. The improvements in production have continued to the year 2001, although not at the rate of the improvement in the 1994 to 1998 period. At the present time, the field is producing over 20,000 barrels per month of oil, and this production level is being sustained. Targeted recovery factor is now about 20% of OOIP for the best central part of the reservoir. Based on continued good chops well performance. 5.3 Individual well behavior. Figures 5.2 to 5.5 are typical wells from the Luseland field. More individual well plots can be found elsewhere. Some comments are warranted for each well to explain the data. Well 91 is the best of the 6 horizontal wells drilled in the early 1990s. Within a year after production started, a strong trend in increasing water cut was accompanied by a drop in oil rate to below economic levels. Workovers and other attempts to establish good oil rates did not succeed, and the well was finally abandoned in 1998 based on a well cost approximately 4 times that of a vertical well. 1 million Canadians vs. 250,000 Canadians in 1992. On the average price of oil and on typical operating expense, even the most productive horizontal well was not an economic success. Unfortunately, this is not unusual in heavy oil. Well 5.4 Figure 5.3 is a vertical well that always had relatively high water cut from the first day of production. It was converted to chops and therefore subjected to more aggressive drawdown. Generally, this would be expected to immediately accelerate the rate of water cut increase, but the opposite happened. For the first decade of the well life, the average water cut was approximately 50%, but in the period 1994 to 1998, the water cut dropped to about 30 to 35%, 1 part in 3. At the same time, the oil production rate changed from 22 barrels per day to over 100 barrels per day. Where 14.7 figure 5.4 produced for the first 12 years of its life on a reciprocating pump. It actually showed a decline water cut, going from a WOR of above 1 in the first 2 years to a value of 0.25 in the period 1991 to 1993. At about 1994, it was converted to chops, and oil production rates began to rise substantially, initially without the water cut increase. However, sudden water breakthrough occurred within about a year. At the end of 1994, attempts to restore oil production have not succeeded. These were produced just less than 100,000 barrels of oil. It is widely accepted that for a cheap vertical well in this heavy oil field, payback and operating expense are met if about 30,000 to 60,000 barrels are produced, depending on price and workover requirements. Therefore, this well was likely a marginal money maker for the company, providing that it did not require a large number of workers. Where 1816 figure 5.5 produced on a reciprocating pump for a number of years at a modest rates that increased to 40 barrels per day before water breakthrough took place, resulting in the well being shut down for 3 years. In late 1993, the well was converted to chops and the oil rates climbed to over 100 to 200 barrels per day, and stayed there for over 3 years before oil production once again began to drop off. However, during the oil rate drop-off in 1997 to 1998, the WOR did not rise. This indicates that oil rate loss was linked to depletion of the reservoir energy in the well vicinity. GOR values were stable for the period marked on the plot, but the GOR values began to rise in 1997 at the same time that the oil rates began to drop. By the end of oil production in 1998, GOR was 5 to 6 times higher than in 1996. It appears that a continuous gas phase developed at about this time, and this caused a depletion of the foamy oil drive mechanism in the well vicinity. This well produced about 250,000 barrels over its life, about 80% of this in the second phase of the well's life after it was placed in chops production. Thus, the chops phase was highly profitable for the company in this well. 5.4 Field behavior. The total historical liquid production values for all the vertical wells in Rusland are plotted in Figure 5.6. Clearly, the examples shown in the previous figures are not the best in the field, by any means. Figure 5.6 include not only the 30 original wells that were converted to chops, but also the higher-risk wells drilled in the 1990s on the flanks of the structure. Generally, the high-risk wells and the new wells plot to the left-hand side of the diagram, and carefully examination shows that most had very high water cuts, which suggests why they were generally shut down after a short production period. The figure shows that the overall average cumulative oil production in these wells is about 3 times the water production. If the high-risk wells and all wells drilled since 1990 are removed, the average oil produced is on the order of 230,000 barrels per well to 1998, over 300,000 to 2001, based on verbal statements from the operator. For those wells with production in excess of 400,000 barrels, the recovery ratio for their individual drainage areas is approaching 20%. For the overall field, it was approaching 11% in 1998. Figure 5.7 is a plot of the average monthly water rate versus the average monthly oil rate, without correcting for the total oil rate. This is no obviously correlation between the two rates. However, if the water-oil ratio WOR is plotted against the oil production rate, as shown in Figure 5.8, a definite hyperbolic relationship exists. This later plot shows that the better oil wells are generally the wells that produce the lowest amount of water. This makes sense, and yet there are exceptions. The 3 wells circled have shown a reasonable oil rate despite a high WOR. In fact, there are not attempts underway in Alberta and Saskatchewan to produce heavy oil in chops field using water flooding. These efforts have achieved additional oil production, albeit in modest amounts. Note that conventional predictions using textbook equation would never justify water flooding in such field, but the reality, the heavy oil, is often different than the theory. This is also the case with CHOPS process. Using conventional oil production prediction method would lead not to no vertical wells ever being drilled in these reservoirs. CHOPS water flooding projects have proven economical in that operating costs are more than met by the additional value of the incremental oil produced, but the amount of the incremental oil production is not large, seldom more than 1 or 2 additional percent of OOIP. In the fall of 1999, water flooding in a 10,800 cp heavy oil deposit north of Leominster was attempted using a pressure placing approach to moderate viscous fingering instability. The pressure passed water flood showed down the sharp production decline in the CHOPS field, and this prolonged the life of the field. At the same time, water production increased, and individual CHOPS well behavior in the offset producing wells changed, with large sand cut observed for the 6-month period during which pressure passing was used to inject water. The netback to the company was about $58,000 per month after all additional costs were paid. 5.5 Horizontal vs vertical wells. This is not a trivial question, and the answer is not obvious. On the basis of production data in heavy oil wells, it might seem obviously that horizontal wells should be economical, even lucrative. The logic goes something like this, using Luseland as an example. Verticals penetrate 10 to 15 meters equals 30% sand. SO is 0.85, as in Luseland without deliberate drops. These wells can produce 15 to 50 barrels per day using reciprocating pump in a conventional oil reservoir. 1,000 meters horizontal well might produce 5 to 8 times this amount, 100 to 300 barrels per day. Thus, 1 million horizontal well will produce at least 40,000 barrels per year, and with 3 years production, be economical. At least somewhere, producing over 100,000 barrels per year can be expected, giving excellent profits. What is the flaw in this logic? It is that the production mechanism in the second step is assumed incorrectly to be the same production mechanism as for conventional oil. Darcy-dominated flow without any ancillary positive influence from sand influx. This then leads inexorably to the remaining points of the logic, so that a mistaken final conclusion is reached. In the Albert and Saskatchewan portions of the HOV as demonstrated in the Luseland field case, it is possible to find many reservoirs that have been producing 15 to 50 barrels per day per well for many years using reciprocating pump. However, more careful examination of production practices will show that all these wells have small amount of sand that enter the variable continuously with the oil. If the sand is stopped with a screen, slotted liner, or gravel packer, the oil rate will drop to only a few barrels a day. It is this latter figure, 2 to 10 barrels per day sand-free rate, that must be used in the logic sequence states above. This leads to predicted horizontal well rates closer to 50 to 100 barrels per day, although some fields do actually produce much higher rates than this from horizontal wells. It is usually found that these successful cases are in the lower viscosity range of Alberta heavy oils, below 1,500 cp. Horizontal wells are almost invariably completed using slotted liners with slot wide of 40 to 100 um. This serves the role of the excluding formation sand. Thus, in horizontal well in heavy oil, sand is largely prevented from entering, and the production enhanced aspect of chops never develop. If the correct production value is used in comparisons, sand-free oil production rate from a vertical well, it will lead to conclusions that seldom can sand-free horizontal wells be better producers than vertical chops wells in heavy oil deposit. In fields such as Pelican Lake and Amber Lake in the Alberta that have been exploited with horizontal wells, the operators report that There is a small amount of continued fine green sand in grass. This is probably the reason that this field was successful, providing rates that approach 300 to 500 barrels per day initially, although declining at a rate of 25 to 40% per year. Is there additional proof of the comparative behavior of horizontal wear, whereas vertical chops were beyond the Luseland case? Fortunately, even though it was expensive for them, a number of operators have tried horizontal wears in precisely or omit both words. The same areas where verticals were drilled and chops was implemented. Several of these additional case histories will be briefly presented. The reservoir parameters for these cases are roughly similar. Porosity of almost 30%, temperature in the 20 to 30 degree range, oil viscosities in the 1000 to 10,000 range, absolutely permeability in the 1 to 4 Darcy range, although there are invariably minor differences in oil saturations, thickness, depth, initial pore pressure, bubble point, and so on. These differences among reservoirs and producing fields will not be discussed in detail because the comparisons to follow are based on wells in a small geographical area, no more than a section 2.5 kilometers in each case. This means that the geological parameters and reservoir parameters were virtually identical for the horizontal and the chops well. 5.5.1 Limbur's field horizontal the chops comparison. The Lindenberg area in Elba, north of Township 53, has hundreds of wells producing from several formations. The specific data shown here are from wells producing from the Rex Formation. Figures 5.9 and 5.10 are the examples chosen to allow a direct comparison of wells in the same 2.5 kilometers listed in table 5.3. This table shows us section 25 Limburg vertical and horizontal wells. Here is 4 vertical wells and 3 horizontal wells, and we can see the production. The vertical wells is more than horizontal wells. Yes. The Rex Formation, Grand Rapids Formation, equivalent if the Cold Lake area terminology is used. It is a Cretaceous fine green, aquatic blanket sands containing oil of viscosity about 10,800 cp under reservoir conditions with oil saturation values of 0.85 to 0.88. The thickness of the producing zone is from 2 to 9 meters generally, and there is no free gas mobile water detectable in the reservoir from geophysical logs. The Rex Formation is in the middle of the Cretaceous group of unconsolidated heavy oil-producing sand. Figure 5.9 shows below average to average vertical chopped wells that produced 119,000 barrels over a life of 11 years. Generally, in this area, it is reasonable to expect more than 150,000 barrels from a single chopped well. The well was shut in, production suspended because of high water cuts in the last 2 months, but it was an economical well overall. Figure 5.10 shows the best of the horizontal wells from this same local area of the Lindbergh field. Note that the oil rate dropped almost continuously from the date production started. This horizontal well stopped oil production almost entirely after only 4 years of production and less than 100,000 barrels of oil production, an unprofitable outcome. Remember that the cost of vertical well was about 250,000, less than a quarter of the cost of horizontal well. Figure 5.11 shows water and oil production for the several wells listed in Table 3. The comparison is based simply on total production to the date at which data were collected. However, the lifespan of the horizontal well is relatively brief, 3 to 5 years generally. Also, comparisons based on a simple set of data can be misleading. For example, there is no information given on types of and numbers of workovers carried out to maintain production from these wells. Nevertheless, given the high cost of the horizontal wells and the high cost of any interventions in such wells, it is reasonable to assume that the conclusion that vertical chopped wells are far more productive and profitable than horizontal wells is valid. An important data point collected from these wells is that the vertical wells, the GOR was moderate and remained constant, whereas in the horizontal wells, such higher GOR plus 5 was observed, and and remained constant. And this tend to increase during the wildlife, even without the beneficial effects of choice processes. One many ascribe the sharp drop of production in the horizontal wells to rapid drainage of reservoir solution gas energy and to reduce relative permeability in the near wellbore of the horizontal well. 5.5.2 Plover Lake Field. The next example is a 10-well group in Plover Lake Field, all from a 2.5 kilometers area. Section 5 in the township. This field is similar to the Luseland field in its basic reservoir parameters, except for somewhat higher oil saturations in Plover Lake. The major points that can be made from this field are worthy of separate and clear statements. All the vertical wells are sand producer, chops well. All the horizontal wells exclude full formation sand production. However, some funds may migrate into the wells through the slot liners. Every vertical well has been a better oil producer than even the best of the horizontal wells. Attempts to improve production in the horizontal wells by steam injection resulted in marginal but not economical justified production improvement. The horizontal wells, in almost all cases, produced more water than the vertical wells. The WOR for the vertical well is about 0.7. The WOR for the horizontal wells is about 4. Table 5.4 contains further detail of the behavior of the vertical and horizontal wells at Plover Lake. As of December 1998, all the horizontal wells had been shut down because of massively declining oil production and high water cuts. Because the vertical chops well have been on production for much longer times, it is also valuable to examine the typical production rates. These values over the life of the wells are about 1,050 barrels per month for the vertical and 1,333 barrels per month for the horizontals. However, these figures alone are insufficient for a rational comparison because in the period 1994 to 1996, the vertical wells were placed on chops production after 12 to 13 years on slow oil production with only small amount of sand ingress. In other words, the vertical wells have production histories similar to Figure 5.3b. Care is necessary in comparisons. This table shows us the Section 5 Plover Lake field where we can see there is 4 vertical well and 4 horizontal well, and we can see the vertical well produce more than 15 years, and horizontal well just 3 to 4 years. And the oil production show us the vertical well is much better than the horizontal well, because the horizontal well the horizontal well life is less than the vertical well. Cactus Lake Field. Cactus Lake Field in this area is just east of the Albert border, about 110 kilometers south of Lloydminster. Production is from unconsolidated fluvial channel sand ranging from 22 to 30 meters thick, with 60 to 90% of net pay in the interval. The channel is 1.5 to 2 kilometers wide and is referred to as the McLaren Formation, the uppermost of the Cretaceous Mannville Group heavy oil zones. On average, it is medium-grained, but there are many fine-grained oil-free trees in the upper 20% of the reservoir, and several in the lower 50% as well. Because these are channel sand, there are lag deposits comprising coarse green sand and gravels in the lower part. All factors being equal, one would expect the permeability of lag gravel deposits to exceed 5 to 8 dc. This McLaren Formation channel sand has a permeability of 2 to 5 dc reported average in the pay zone. The sand is saturated 0.85 with about 5,000 cp heavy oil. There are a few small free gas caps locally, and in the bottom of the channel there are zones of free water. However, both the small gas caps and the water zones are particularly isolated from the central, richer pay zone by bands of lower permeability deposits. The 8 horizontal wells listed in the table 5.5 are all 1,000 to 1,200 meters long, spaced 200 meters apart. The The wires were intended to be upper wires of a double-wire, steam-assisted gravity drainage system, but initial tests on the wires seemed to justify a non-thermal production phase. The horizontal wire were drilled in the upper part of the formation to keep them farther away from active bottom water in order to operate the gravity wires under small gradients and thereby achieve higher production rates. The single vertical wire is the same 2.5 kilometers area as the 8 horizontal wires and is operated. This table shows us the section 14 and 15 Cactus Lake field wires. You can see the months on production of this wire remain maybe 4 to 10 years, and the production is not the same. Someone is much better and someone is lower. Figure 5.13 contains a plot of water and oil production from these wells. Cactus Lake Field is one of the most successful cases of horizontal wells in heavy oils, with viscosities greater than 1000 cp. Nevertheless, the single vertical troughs were had proved to date to be better overall than 4 of the horizontal in terms of total oil production, but not as good as the other 4 wells. It is important to remember, however, that vertical wells are far cheaper to drill and to operate in terms of intervention activity costs. In addition, the vertical trough well has produced at a more favorable WOR than the 4 best horizontal wells. 5.54 Evaluation of non-thermal horizontal wells vs vertical trough wells. Essays try to explain prediction difficulties for horizontal wells in terms of mesh refinement in numerical modeling efforts, as well as a lack of sufficiently refined geological models. Their arguments are unconvincing. Belief compared horizontal wells with offsetting vertical wells in an effort to explain more clearly the risk involved in horizontal well assessment. He noted that for heavy oil, there was a very wide scatter of horizontal well performance as compared to that of offset vertical wells. The 4 cases presented in this chapter seems to reinforce this observation. The writer believes that horizontal wells are not inherently more scattered in terms of their production performance, although a long horizontal well clearly has a greater chance to being close to active water and therefore is undoubtedly more prone to calling if it is operated as a delta-P-dominated wire. See previous footnote. Rather, the writer contends that operators still do not understand fully the dominant physical processes involved, and therefore make use of horizontal wires in many circumstances where they are not advisable. These articles and many others based on conventional interpretations and simulations fail to address the issue of fundamentally different production mechanism in vertical choke wires and in horizontal wires without sand production. Choke wires produce sand and therefore benefit from the aforementioned production enhancement mechanism, whereas horizontal wires are not in general designed to produce sand. This choke mechanism, sand liquefaction, foaming oil dry, etc., are not incorporated into the reservoir simulations currently in use. Therefore, a rational evaluation of their impact using production predictions based on physical processes is not available to the planning engineers. Rather, the only reasonable predictive approach at present is prediction by analogy, using similar cases to project likely behavior of the case being studied. For this approach to be effective, the planner must understand by physics in depth so that proper analogies can be developed. In general, this has not been done, and many failures or projects of low profitability have resulted. Nevertheless, other successful horizontal wells in Pelican Lake, Amber Lake, and Argentine area in the Websco deposit have produced reasonable amounts of oil in the range of 1000 cp viscosity from thin zone on the order of 4 to 7 meters thick and without active bottom water. Given the data present to date, it is clear that a more practical methodology is needed for well evaluation in heavy oil reservoirs. The following practical methodology is suggested. Carry out a comparison to other heavy oil reservoirs, particularly in Canada, where the knowledge basis is vast compared to other areas in the world. This comparison must seek to identify and establish the best analogies available in the data bank. If the reservoir is truly and unconsolidated, concemented sandstone, with no free mobile water zone in the reservoir interval, chops may be a viable and profitable method if needed. If deemed suitable, chops trials should be attempted to virgin zone and have not been neglected or treated with another technology. For example, steam injection, steam driver. If the reservoir sandstone is slightly cemented, technologies other than chops are more likely to succeed. Nevertheless, if the cement, if the cementation is weak, a period of deliberate sand production may be beneficial for their productivity because of the enhanced permeability zone generated. If chops appears feasible, it is reasonable to test field production behavior with several pilot wells before adopting field-wide application. A minimum of 4 or 5 test wells seems reasonable before a field development decision is made. A chops pilot test requires 1 or 2 wells and is likely to cost about 1/4 to 1/2 of a horizontal well test. If chops is feasible, there is little economic incentive to pursue more expensive solutions, such as thermal stimulation. On the other hand, if properly executed, executed tests show that chops is not feasible, evaluation of alternative heavy oil production approaches must be carried out. The alternative options at this time are thermal approaches using high delta P techniques such as cyclic steam stimulation. Although this group of technological alternatives requires excellent reservoir conditions and has its own set of operation difficulties and costs, they are in general not recommended. Gravity-based thermal methods such as SAGD, VPATs, or some combination of the two. Non-thermal approaches involving long horizontal wells. This is the favored production method in Venezuela, where with the installation of many laterals, it has proven successful economically, but is likely to result in only 10 to 12% OOIP recovery. Pressure pass flow enhanced using horizontal producers and vertical excitation wires can be used with most technologies to enhance flow rates or to help stabilize water injection in heavy oils. Included in the Appendix 3 is an article comparing Canadian and Venezuela experience, and the reasons why the Venezuela projects have pursued multilateral horizontal wells rather than exploring the possibility of troughs production. However, it appears that the upper strata in the Fija there with about 30 to 40% of the resource are not suitable for the long horizontal well approach, are too thin for thermal method, and therefore represent large potential applications for troughs. 5.6 The mathematical simulation of troughs. 5.61 Non-conventional processes in troughs. Mathematical modeling, numerical simulation. Numerical simulation of troughs for predictive purpose is particularly challenging because troughs involves a series of processes that are not conventional addressed in reservoir simulation. There is a solid to liquid phase transition of the metric stresses and stress changes play a major role in sand destabilization and liquefaction. Conventional assumptions of phase saturations based on compositional simulation and thermodynamic equilibrium are not justified. Much of the transport process is dominated by slurry flow rather than by diffusional mass transport alone. Geometrical boundary conditions. Moderate zone size change continuously. For more physical parameters are needed than in conventional simulation. In particular, many geomechanical and slurry parameters are needed as well as Darcy flow parameters. General uncertainty remains high regarding of the appropriate value of physical parameters and their relationships because of sampling and testing difficulties, and the processes involved phase transition, slurry behavior, and invariably strongly nonlinear and coupled. making it impossible to write simple behavior laws. Nevertheless, a decade of effort of developed simulation of tropes has achieved substantial progress. Adequate simulation models are now available, and progress continues. The major physical processes are not discussed, but such a discussion will necessarily suffer from a lack of detail. Delving into the detailed physical and mathematics of tropes, analysis requires reference to the literature and a considerable amount of dedicated analysis. 5.6.1.1 Liquefaction of sand. Sand liquefaction is phase transition from a solid to a liquid. Such a phase transition accompanies all Tropes process. In this phase transition, porosity plays the same role as temperature in the melting of a solid. In fact, a rigorous treatment porosity must be treated as a thermodynamic state variable in a manner similar to temperature. Unfortunately, unlike in melting of a single phase, there is not specific melting porosity that forces the sudden jump from a 30% porosity solid to a 90 porosity liquid. The process is much more complicated, even more complicated than the melting of an alloy of different metals. The liquefied state is defined as the condition that exists when grains do not form a continuously linked array. Liquefaction implies that delta equals zero and delta equals P. The reservoir is a porosity of about 30%. The outflow at the wellhead contains about 1 to 10% sand and substantial quantities of free gas. Thus, it has a porosity above 90%. In changing from 30% to above 90 porosity, the system in the reservoir must pass through all intermediate inter- intermediate porosity, and the changes in physical properties are accordingly huge. Figure 4.14 is an attempt to show how the dominant physical process change with porosity to achieve the liquefaction porosity of about 50%. The sand fabric must dilate after liquefaction. A dense slurry exists where substantial internal energy dissipation take place through collation and sliding between grains. Even though the grains are not in sufficient state of contract to transmit the compressive metric stresses. After more dilution with liquid and perhaps some gas bubbles, uh, dilute slurry is generated. At this point, green collision energy dissipation becomes negligible compared to the level of viscous energy dissipation in the fluid phase. Even neglecting the completion of a dispersed double phase in the slurry, one phase transition and three or four separate regimes existed in the porosity domain encountered in troughs. Elastic deformation, plastic deformation, the phase transition, then slurry flow, uh, dilute slurry flow, then sand do not spontaneously liquefy under stress. The grains are held in a three-dimensional array with high contract forces, normal and shear forces that cannot be overcome by seepage forces. This fabric must be uh, perturbed and dilated, which requires a large reduction in confining stress and an increase in shear stress. Because all of these changes are linked to the mechanical state and response of a reservoir fabric. Geomechanics factors are of primary importance up to the point of full liquefaction. Thereafter, hydrodynamically become dominant. 1.6.1.2 The enhanced permeability zone near the variable where sand is liquefied. Permeability cannot be defined in the about 45 porosity zone. It exceeds 15 to 20 Darcy for 100 to 150 sand, where intact sand still exists in the reservoir. A typical permeability is 1 to 4 Darcy, perhaps of equal importance as the reservoir sand dilates. Pore blockage clears as Fullerton's gas bubbles have less and less effect on the permeability. If a compact growth zone exists, an average permeability linked to possibility can be defined, but this implies that the mathematical simulation gives a reasonable estimate of porosity, and that porosity is homogeneous, not channeled, and at the same physical scale of the mathematical this characterization used. These assumptions remain unsubstantiated and are unlikely to be true. Alternatively, some simple function of radius may be used to describe physical properties around a chalk sphere. Figure 5.15. If the K-enhanced zone is highly irregular in shape, a few channels define a block average permeability at an instant in the simulation process is not only a problem, the value will also change with the early time step. Apparently, there is no easy way to determine the permeability because of the non-homogeneity of the region surrounding the well, and the general uselessness of well test. Some work shows that a simple model can capture most of the permeability enhancement effects. Sensitivity analysis show clearly that although a model continuous change in permeability gives time derivative derivative plots that are quite different than a skin model. Skin is a zero thickness flow impedance zone. Result can be approximated by a multiple zone composite model. However, each additional zone in a composite model has two additional unknowns, and once the number of zones exceeds two, the number of unknowns becomes so great that any solution by inversion or curve matching is no longer realistic. For example, two cylindrical zones around the well giving 8 total unknowns. 3 compressibilities, 3 permeabilities, and 2 ready. Performing a statistical analysis on well performance to find these values in the case of chalk well is essentially a futile exercise because of the lack of constraints on the process. To the writer's knowledge, all such efforts have failed. 5.6.1.3 Forming oil behavior. The physics of forming oil has been examined in detail in recent years. Many scientific and technical issues that are currently being in laboratory and research groups in Albert and will gradually affect and improve the mathematical simulation of foamy oil behavior. This includes obtaining a kinetic X solution rated for CH4 from cold heavy oils, an extremely challenging experimental task. Verification of the hypothesis that a continuous gas phase does not develop in tropes. Otherwise, another explanation for the constant GOR values over many years of production will have to be developed. Understanding if the bubble induction zone is physically linked to a zone of sand dilation. Perhaps bubbles can be created only when sufficient new local volume is created by the dilation process. Quantifying of the efforts of bubbles on sand permeability relative to oil flow conformation and quantification of various other physical processes around trough wells. 5.6.1.4 Slurry flow. The mechanics of dense and dilute slurries of solid is a complex issue that is not yet resolved for high concentration slurries where internal energy dissipation through collisions can take place. It will not be discussed in detail here, but the subject has been studied in the laboratory and from a theoretical point of view. I will show 5.6.2 Conventional approaches to simulation. Conventional simulation without stress complete attempts to account for the efficient stress change efforts through prediction of volume changes using compressibility delta V equals delta V and plus C and delta delta. To use this fundamental and correct relationship in particle simulation, a further assumption is made that delta equals minor delta P, where the changes in pressure is calculated as part of the mathematical simulation. This is a flawed assumption. A change in pressure does not lead to the identical and opposite change in effective stress. The relationship is more complex and must be calculated in a rigorous manner using the compressibilities of the physics. Moreover, in all conventional flow analysis, it is implicitly assumed that boundary stress remain constant. Terms do not even arise in formulation of flow equations. However, consider what happens near a vertical wear. As the wear is produced, the pressure near the wearable drops. Therefore, delta increases and a small value changes must occur. This means that the rock near the wearable shrinks slightly, but since the overburden rocks have rigidity, the vertical total stresses are redistributed. The total stresses are clearly not constant. Hence, the common assumption is immediately invalidated. Analysis of this effort shows that errors in flow rate predictions are as high as 50%, and that the errors are dominantly during the period of early flow, which is usually the domain that is analyzed in the reservoir evaluation. Furthermore, one may note that stress action during early depletion, even during extended production tests, can delay the onset of massive compaction. This was the case for the Ecofisk field in the North Sea. Extend production test field to identify compaction and necessary platform height to resist wave action over 15 years was thus underestimated seriously, requiring expensive platform jet up activity costing about $500 million in the late 1980s. Other assumptions inherent in conventional simulation method mentioned above should be revisited as well. In particular, the standard assumption of local equilibrium is probably insufficient for heavy oil because of the extremely slow diffusion rates. Uh, a kinetic model is needed. In a kinetic model, the rate of gas evolution from the liquid phase is analyzed at each time step so that amount of free gas at any time can be calculated. In many analyses, attempts to history match the behavior of laboratory samples are carried out using conventional mathematical simulators. However, these exercises usually involve many free or ill-defined parameters, or else the user will fix parameters, solubility, gas contents, bubble points, relative permeability, uh, compressibilities, and physical unreasonable value in order to improve the statistical fit to the real data. Can this effort using freely and adjust parameters and laboratory processes in which the boundary conditions are totally different than the case of value in design? For this to be the case, There must be direct and useful relationships with mechanisms and the large-scale systems alterations that take place during chops. If a conventional simulator is used, process such as growth of compact or a channel zone cannot be included, except empirically in an effort to fit the history and match the data. For example, it is possible to increase the radius of high K-zone purely as a function of amount of sand produced from the chops well. This function, relating radius and volume of sand produced, is arrived at purely uh, and is based on the assumption that this is indeed the dominant physical process in chops. Is it valid to attempt to history match chops in specific cases if several first-order physical processes such as the effort of stress, sand dilations, and liquefaction and salary flow are absent from the model? Furthermore, it is valid to use this calibrate model to predict the further behavior of the whale or other whales in the field. The answer is not all clear, but the direction of the simulation is clearly away from calibrated conventional simulation to more rigorous coupled geomechanics simulation based on physics rather than spatial relationship. 5.6.3 Stress flow, coupling, and physics-based modeling attempts to develop analytical and semi-analytical solutions for chops where production behavior are hampered by the massive non-line and complexity of the process. Nevertheless, the compact growth and channel models considerable progress and being achieved. These models essentially had their origins in early attempts to understand stress, dilations, and yield around circular opening. The sand flux models are all based on introducing aspects of stress, sharing in induced dilations and concomitant permeability increases, with necessary simplifications such as 2D geometry, ideal elastoplasticity, local homogeneity, limited provision for slurry flow, energy dissipation, and so on. In the simplest case, stress changes and flow behavior are expressed in vertical equations and assume plane strain in z direction. Overburden stress redistribution is not explicitly incorporated. In this case, flux equations reduce to quasi one-dimensional forms. The Gell-Mann family of models links the drawdown rate of the weir to the magnitude of sand flux. His model prediction of an initial high then decline sand flux combined with slowly increasing then slowly declining of oil flux correspond with observed field behavior. However, no semi-analytical model can simulate the initial of sand liquefaction and make a period of prediction of sand flux and oil rate increase based solely on a set of initial conditions. Material parameters and constitutive laws. Many assumptions have to be made, and the models must be repeatedly calibrated to sand production history to help develop realistic predictions. Recent work is moving toward more general numerical simulations based on a coupled stress flow formulation solved with the finite element method. These methods are far too complex to discuss here, but it should be noted that most aspects of the TROPS process, with the exception of the slurry flow component, are now being incorporated into modeling on a relatively sound physical basis. This is yet a considerable distance to go to achieve full simulation capability of TROPS process. And substantial uncertainty will always remain because of the large number of poorly constrained variables in this complex process. Finally, it is worthwhile noting that issues such as stress arching, stress redistribution, fabric involution, changing porosity and permeability during deletion and liquefaction, and slurry flow, mixture of bubbles, liquids, and sand grains can be studied using the discrete elements method, where individual particles are allowed to interact and fluid flow forces can be included. These methods promise to generate insight into issues such as the capillary changes and destabilizing of sand arches, and extremely difficult problem that is not amenable to continuous mechanics approach. However, these are physical-based models, not design models. that use volume grid properties, and they are not likely to be used for mathematical reservoir simulation. Okay, next, to make us understand clearly different fluid behavior, I will show us a video to talk about the oil phases behavior. Yeah, let's see the video together.
Hello. This video will be a brief introduction to the phase behavior of hydrocarbon oil and gas mixtures. And I'm going to do this by illustrating some phase diagrams that you typically encounter for oil and gas fields, and talking about different types of hydrocarbon accumulation, how I define what an oil field is, how I distinguish it, say, from a gas field. And so what I'll do is I'll use the whiteboard as before. That. Okay, so what I'm going to start with is by drawing a phase diagram for two axes here. This is pressure. This is temperature. So we have two axes here. This is the pressure of the reservoir. This will be the temperature of the reservoir. And many of you may be familiar with what a phase diagram for a mixture of chemical components looks like. And so I'm going to draw it here, and then I'm going to explain all the different features. Okay. So what you have is you have a finite region of temperature and pressure where two phases are present in equilibrium. And those two phases are going to be oil and gas. Okay? Liquid oil phase. Then at very high pressures and low temperatures, things tend to be liquid-like. So here we're going to have a single phase here that's going to be oil. Okay? That's okay. And then at very high temperatures and low pressures, things tend to be gas-like. So this will be gas here. Okay, so this is an example of what a phase diagram for an oil and gas mixture might look like. Okay, so let's now imagine that we have an oil field, and this is why I'm using my green pen here. So imagine that we discover field. This is my initial conditions. Okay, so what's shown here, green spot, are the initial conditions. So here's my reservoir. It's initially at a high pressure and at a higher temperature than we'd see normally at the surface. So in order to make that clear, okay, I can also indicate surface conditions. So I can find a different color for this. This will be the conditions at the surface. So this is the surface. Okay, so the surface is lower pressure and lower temperature. And in fact, generally, as we're going to explain, it's in the two-phase region. Okay, so now what happens when we produce our oil field? If we're producing under primary production, so we're simply extracting the oil, not injecting anything, then what's going to happen is the pressure is going to decline. So we're going to follow in the reservoir this trajectory, right? We're going to go down. And it may not be 100% clear as I've drawn that, but the temperature in the reservoir will stay constant. There's an enormous heat capacity in the rock. I'm not injecting or doing anything, so that temperature will stay the same. So that's actually supposed to be depicted by a vertical line here. Now, what you're going to find is what happens when we go from a single phase, so we have oil existing in the reservoir, in the pore space of the rock. When we cross this line is called the bubble point line. Okay. That point. Okay. And this pressure here is called the bubble point. Okay, so the pressure, there's a pressure at which you enter the two-phase region. And that pressure represents the pressure at which in the reservoir you start getting bubbles of oil evolving in the pore space. And that's a problem when it comes to oil production, because you start producing this gas. Once those bubbles of gas connect in the pore space of the rock, gas has a much lower viscosity than oil, so it flows more readily and it's preferentially produced. So you have a reservoir that was initially full of oil, you drop the pressure. Now, oil isn't a terribly compressible fluid, so there's a small amount of expansion, okay? Then this gas comes out of solution, the gas is preferentially produced, and you have a field that's essentially just producing gas, and you've left behind the more valuable component, your liquid oil. Okay? So in terms of oil production, this is a bad thing to do. I mean, if you're going to pick up anything from these lectures in how to operate an oil field, rule number one is actually try and maintain the pressure above the bubble point, so you have a single phase oil that's flowing into your well. Okay, so that defines an oil field. Now what happens when you bring it to the surface? Well, what happens here in a trajectory, which I'm not really showing because it's not of interest in this class, is you will go from the conditions in the reservoir to the conditions in the surface, and that will you do as the fluids flow up through the well. And clearly, as you can see, you're now in the two-phase region. So when you're at the surface, you will be producing both oil and gas. And you do that even if underground you've only got one phase, one liquid phase underground. So at the surface conditions, you produce both oil and gas. That's not a particular problem. You have to separate out the oil or gas, and then the oil you sell and gas, obviously, you can sell or re-inject into the oil field. In the wellbore itself, the idea that you've got these two phases is actually good for production because the gas has low density. The bubbles of gas actually move upwards and they entrain the oil. So in fact, they help lift the oil from the deep reservoir to the surface. So that's an oil field. Now, you might say, okay, well, that's fine, but what's this strange black spot I've drawn on the diagram? Well, those of you who are familiar with phase diagrams will know what that indicates. What that indicates is what's called the critical point, and let me explain. So when we hit the bubble point here, okay, we see bubbles of another phase, and we call them the gas phase because it's less dense. You can actually you can take fluid samples from deep underground. Okay? You have your fluid contained at the initial conditions in the reservoir, which you have measured, so you impose those in the laboratory, and then you drop the pressure, and you see bubbles of gas, and you know that they're less dense because those bubbles rise. But what you notice is if you were to look at this at higher and higher temperatures, the gas that comes out tends to have a more and more similar properties to the oil. The composition and the density become more oil-like. The oil, because you're increasing the temperature, is becoming less dense, right? It's beginning to expand. And the first droplets of gas that come out tend to be more and more, one might say, oil-like. And at the critical point is actually technically when you switch now from producing droplets of or bubbles of gas to droplets of oil. So exactly at the critical point, when you produce the two phases, they are identical. Now you might say, well, that doesn't make any sense. How can there be different phases? It's only a point. As you move away from this, you see distinct phases. So on this side of the line, you have what's called the dew point. And the dew point is where when I drop the pressure, you have one phase, then you see droplets of another phase, and that other phase is more dense, and you can see it. It will sink in your PVT cell, pressure, volume, temperature cell. So that's what you're measuring. So it will tend to sink, and when it sinks, then you know that that's the oil phase. So this is the dew point, and you're basically producing a field that is now more gas-like. Okay. So let me explain that in a bit more detail. So first of all, the word dew. The pronunciation in English is a bit strange because it begins with a D, but we actually pronounce it like the first letters a J. In American English, it's a little bit more straightforward, dew with a D. What is dew? Dew is if you have a cold night and the air is quite humid, which I can tell you is the case most of the time in England. Then in the morning, what you notice is the water vapour has condensed. And where does it condense? It condenses on things that are cold. It condenses on the grass. Okay, you also tend to get condensation on windows, for instance. But certainly the condensation on the grass is called dew. Okay? So that's where the word comes from. What it's used here is to refer to the condensation of liquid, in this case oil. It has nothing to do with water. And it's also a little bit counterintuitive because here we're having the condensation of a liquid as I'm dropping pressure. It seems sort of the wrong way round. We're much more used to considering the condensation of a liquid as we reduce temperature, which would actually be moving in this direction, phase diagram. So now let's describe the types of field that we can now obtain if we are at a higher temperature on this diagram. So actually I'm going to start with the easier case, right, which is here. What happens if I'm right out here? If I'm right out here, imagine my initial conditions are this red spot. Okay. Here, I avoid the two-phase region altogether. Now, as I drop the pressure, okay, the fluid simply expands and expands and expands. So if I'm to the right of this two-phase diagram, I have a gas field. And the way in which I operate that gas field, because I don't hit a phase boundary, I don't get some problems because two phases, and I'll talk a little bit later about the problems with two phases when we hit the dew point, but let's keep with this simple case first. That's the way of operating a gas field. So if I have a gas field, which is defined now, not as, oh, it's a gas or it's got this sort of composition or some sort of, vague rule. What it means in terms of the phase diagram is that I have a hydrocarbon composition in the subsurface. And as I drop the pressure at constant temperature, I don't hit a phase boundary. So it stays gas. And so the way in which I produce this field is I just drop the pressure. So a gas field, I drill wells, I drop the pressure. End of story. And because we start with a pressure that's typically hundreds of atmospheres, we can't all the way go down to 1 atmosphere because then there's no driving force for flow, but we can normally go down to a few tens of atmospheres. We can have a 95% drop in pressure. Because roughly speaking, and we'll do this more precisely in a moment, the amount of gas, the mass of gas, the moles of gas is proportional to, for a given volume is proportional to pressure. We can have a 95% recovery. Okay, so that's pretty good. Now, what happens at the surface? If we notice at the surface, we're here, we're colder. So at the surface, you do produce some liquid. Now, that's interesting. You bring this mixture to the surface conditions are the surface conditions, and you produce some liquid. Okay. And that's good. That oil you can sell. So that's good news. It's not a problem. That liquid will evolve in the wellbore. And so if we have that such situation, this is called what's called a wet gas. Now, again, just be careful with the language here. It's called a wet gas because the gas, when it's brought to the surface, produces liquid oil. It's got nothing, and I emphasize nothing to do with water. You can produce water from a gas field because there's water originally present in the subsurface. Okay? You can produce water, but that doesn't make it a wet gas. And again, it's a linguistic subtlety. In English, wet normally really does imply the presence of water. In American English, actually, wet is used a little bit more loosely to imply the presence of the liquid of interest. So in this case, because we're interested in oil, a wet gas has the liquid of interest, oil. And I'll give you another analogy. You're in the United States and people might talk about, oh, this is a wet bar. And you might say, well, a wet bar? What do you mean? Someone spilt some water and needs to clean it up? No, it means the presence of the liquid of interest, which obviously in a bar is alcohol. Okay, so a wet bar means somewhere that will serve alcohol. A dry bar will not serve alcohol. Okay? So I'm going to give you another one of those expressions in just a moment about gas. Okay, so that's a wet gas. But we could have another scenario, which I'll do with another colour. Imagine actually that the surface conditions are here. Right? Now this will be unusual if it's an oil field because it means the surface is warmer than the subsurface. So this is only really going to be pertinent to the gas field. You can have conditions where the gas field is here, you bring it to the surface and you're still in the single phase region. Okay. So that means you just produce gas at the surface, and using the analogy I've said for American English, clearly that it means you do not produce the liquid of interest, and so we call that a dry gas. Okay. Now we've got one last case, which I can do in, so let's see if pink works. Okay. This is, it's called a gas condensate. So imagine my initial conditions are here, where the pink spot is. Okay. Now this is a gas field, and the reason why it's a gas field, you might say, well, how do I actually know it's a gas field, is that as I drop the pressure, you hit the dew point. Okay, so at this point, you start producing another phase, you get droplets, a small amount of another phase, and you know that's a more dense phase than the surrounding phase. Those droplets would sink, and so you're producing a liquid. So the surrounding fluid is gas by definition. Okay. So that's a gas condensate, and it's called a gas condensate because in the reservoir, as the pressure drops, you produce oil, condensate. Oil condenses out. Okay? Again, I emphasize this happens in the reservoir. You don't say it's a gas condensate simply because at the surface I produce some liquid. No, I mean, you can do this in a gas field, right? A gas condensate is where you produce oil in the reservoir as you drop. Okay, now, what's the problem there? It's more or less exactly the same as you have with an oil field, which is actually you don't want to cross this dew point. And let me explain why. So what happens is you start producing gas. It's a gas field. Normally that gas will flow quite readily, and so you have a large pressure drop. So at the well, the pressure is quite low. Then what happens is you drop below the dew point near the well where you're producing your gas. So what happens is the liquid drops out of solution and is in the pore space of the rock. So there are two bad things that represents. The first one is the most valuable part of your hydrocarbons is the liquid, right? Because it's a light oil. It's a very valuable oil. And instead of it being produced at the surface, getting it out at the surface, what you're doing is you're leaving it behind in the reservoir. So that's bad news. The second bit of bad news is that oil doesn't flow as well as the gas. So you're producing still just the gas phase, but it's clogging the pore space, right? The oil is in the pore space of the rock. It's clogging, it's restricting the flow of the gas. And that's also bad news. So what you tend to find is you're leaving behind the most valuable stuff, just as you would in an oil field, right? You start producing the gas rather than liquid. You want to produce the liquid preferentially. And secondly, you actually find your gas flow rates are being reduced. So what do you do in a gas condensate field? You might say, well, the obvious thing is a bit like an oil field where you try and maintain the pressure. You inject something, you inject water to maintain the pressure. In principle, that's okay. In practice, it rarely makes economic sense because normally the gas is not as valuable to you as the oil. So in principle, you could do this, but in practice, it's rarely done. So you want to avoid the dew point. How can you do it? Well, there are basically two ways of doing it. I'm going to show you how to do it. Okay. You either try and keep the pressure up here, and the way in which you keep the pressure high is, funnily enough, by reducing the flow rate. So if you've got your well and you're trying to produce very rapidly, you've got a very low pressure here. So what you do is you actually restrict the pressure. You try and keep the pressure at the producing well above the dew point. Okay, so you sort of kick back a bit on production. You then vaporize all the oil, and actually you find then your production rate goes back up again. That will work for a bit, but it doesn't work forever. So plan B is, funny enough, you want to avoid this region, but if you were to go down to this pressure, you'd still be single phase, you'd be all gas. So plan B is suddenly you drop the pressure an enormous amount, right? You try pumping more and more rapidly, reduce the pressure at the wellbore, so that near the wellbore, you're in the single phase region. Now, as you can see in this diagram, that requires a huge pressure drop, and then there's not much pressure drop to drive the fluid to the surface. Okay, so this may not be that valuable, but if you were, say, at this point in the phase diagram, right, where you're just in the two-phase region, this may be something that you would consider. And then people often say, okay, but how do I know what it is? Well, remember, this phase diagram, how do you produce this phase diagram? It doesn't appear by magic. I've done a schematic here. You take fluid samples from the reservoir from discovery, and you measure this phase diagram in a laboratory. I mean, I've just shown you that you'd have a little cell and you vary temperature and pressure, and you'd see where you had two phases and where it's a single phase. So this diagram is something that is measured. You know this diagram. Before you start developing the field, you need to know this diagram before you start. Okay, so that really is the first simple description of the phase behavior. And they're essentially these different types. You can be an oil field, and an oil field is defined by having a liquid oil present, and when I drop the pressure, you form gas. You have a bubble point. You can have a gas condensate, which is a gas field, and when you drop the pressure, you have a dew point and you produce oil in the reservoir. You can have a gas field, and there are two types of gas field. You can have a dry gas field, or you can have a wet gas field. I've explained what you mean by wet and dry. The last description of gas you sometimes might hear, and in fact you might hear this about oil, is sweet and sour. Now, again, it's a subtlety, a linguistic subtlety here in English. Again, in English, sweet normally means the presence of sugar, okay? And sour means a sort of bittery taste. Again, in American English, of course, it can mean the same, but again, sweet and sour, funnily enough, mean the presence and absence of something desirable or undesirable. So when people talk about a sweet crude oil or a sweet gas, clearly they're not referring to the fact that there is sugar present in the hydrocarbons. What they're referring to is there's something desirable about that hydrocarbon as opposed to a sour crude or a sour gas. Okay? And what is the undesirable thing that is in the oil or gas is H2S, hydrogen sulfide. And H2S is highly toxic. You can't sell gas containing this, any H2S. So that H2S has to be separated out from the gas stream. And it's exactly the same as what you have to do with CO2. If there's CO2 present, you have to separate that from the gas stream. So what you normally do is you can use amines and essentially dissolve away the more acidic components, and they're retained, and then you can heat up these amines and the gas is released. And you might say, well, what do you do with this gas that you separate out? That comes at a cost. That's why it's not so desirable, because you have to separate it out. Interesting thing here is the separation of gases, H2S, CO2, has been around in the oil industry since the 1930s. This is not some new wacky technology. If it's just CO2, at present, what people do is just vent it to the atmosphere. But H2S in many places, I mean, H2S is highly toxic, so just venting it to the atmosphere, particularly in a populated location, isn't terribly desirable. So what you do is you compress the gases and you re-inject them down in the subsurface. So in fact, turns out there are hundreds of places in the world where H2S and or CO2 are separated out from a gas stream compressed and then re-injected underground. And you haven't heard about it because it's normal oil field operations and the oil industry gets on with it. And, no one has to make a big fuss or parade about it. Now it's a big issue because of carbon capture and storage, because what we need to do is actually capture a lot of CO2 and inject it underground. And so people say about carbon capture and storage, oh, it's this new wacky technology and we don't know if it's ever going to work. Well, I'm sorry, guys, but the oil industry has been doing it for decades. Right? And it's been doing it for decades, sort of, I would say, under the radar, because it hasn't been done for climate change reasons. Okay, so that's my first phase diagram, and that looks fine. One thing that may be a little bit misleading about it sort of gives the impression that you have different types of field, an oil field, gas condensate, gas field, or a given hydrocarbon mixture, and it's just dependent essentially on the initial reservoir temperature. Now, that is true, right? You can have a hydrocarbon mixture that at a higher temperature would move from being an oil field to a gas condensate, but that's not the major difference we see. The major difference we see is we have some fields that are essentially all methane, so they're dry gases. Right? It's gas at the subsurface and it's gas when it's brought to the surface. And you have some hydrocarbon accumulations that are essentially tar-like. They're virtually solid at room temperature. And so they're heavy oils and they contain long hydrocarbon chains. And so principally when we're looking at different types of field, this diagram isn't really the diagram we want to do. So what I'm going to do now is I'm going to draw one other diagram that actually shows the different types. Okay, so that will be here. I'm going to clear this diagram and then I'm going to draw another one. So it's going to be the same. It's going to be by pressure temperature. And what I'm going to do here, right, is I'm going to have a spot here, which is my initial temperature and pressure. Right? That's my initial conditions. And I'm going to put my surface conditions here. Pressure at the surface, temperature at the surface. And I'm going to keep those fixed. Okay, so imagine I keep those fixed. All right. Now what I'm going to do is I'm going to draw different phase diagrams for different types of hydrocarbon accumulation. Right. So let's do the first, which is, this will be an oil field. Okay. Okay, so this is my oil field. Right. And you can see here, you go down, that's the bubble point line. The critical point is to the right. Okay, the surface conditions are in the two phases. Okay, so now let's do some different examples. Okay, so let's start with dry gas. So if we have something that's almost entirely purely methane, okay, it won't be 100% methane, otherwise you wouldn't have a two-phase region. But imagine you have a gas that's mostly methane, may contain some CO2, may contain some H2S, because one of the things I didn't say before is this sweet and sour. That's a word you might hear. There will be a phase diagram, but it doesn't have some special phase diagram. Okay? It's not. You can't look at the phase diagram and say whether it's sweet or sour. So this is dry gas, as you can see. You do not. The surface conditions, the initial conditions are way out here. The surface conditions are here. Basically, everything is to the right of the diagram. So that's that. Let's do a wet gas. Okay. So what you tend to find is your phase diagram, as your composition gets heavier, that is, you get longer and longer chain alkanes in your hydrocarbon. Your phase diagram sort of starts at the top right and then moves down, right? It moves down and to the right. And let's explain why. Right, so a dry gas is mainly methane, right? Virtually all temperatures and pressures we're interested in, we just got a gas. If you have an oil field, here we're going to have hydrocarbons from methane all the way to C10, C20, things that are much more liquid-like. As a consequence, you're going to get a much larger oil region, okay? So large, low temperatures and pressures you're going to have oil present, and you need a very high temperature essentially to vaporize all of that hydrocarbon. So you only get the sort of gas region at very high temperatures. Okay, so that should hopefully explain the sort of shape of this diagram. So we've got dry gas, wet gas. We got an oil field. Let's do the gas condensate. Okay, I can't remember which colours we were using. So these are. So we're going to get something like that, and this is now where the initial conditions will hit the phase diagram, but the critical point is to the left. So this is a gas condensate. Okay. Now I'm going to do one other extreme. Right. Right. Which we hadn't discussed before. It's a simple case. So here's a case of a heavy oil. This will be something where there is in fact no gaseous components present in the oil. It's sort of tar-like. You often see this with shallow fields where there hasn't been much of a conversion of the kerogen. Okay, and so the initial conditions, I mean, in theory, there might be a two-phase region, but actually when you bring it to the surface, you notice it stays in the oil zone. So the heavy oil is something where you don't produce any gas at the surface. So that is fundamentally, the other possibility. Okay, so that is your sort of your phase diagrams as a schematic. As you can see, I've just done this schematically. There are other diagrams in the notes, and you can look at more professional books. The classic textbook in this area is called McCain, right, which looks at the thermodynamics of hydrocarbon mixtures. Okay, I'm just going to show one other case because that's of interest. It's in green. Okay, imagine we have a field whose phase diagram is sort of like this, and where the critical point is very close to the initial conditions. Right. And we could even have another condition, which is sort of like this. Right. And I'll explain these a little bit. So let's imagine that we have the critical point that's really quite close to the initial conditions. Okay? So in this case, this is still an oil field. As you can see, it's to the right, but the critical point is quite close. And that's called a volatile oil. And the reason for that is it's normally an oil field which actually contains quite a lot of lighter hydrocarbons, C1, C2, C3, C4, right? C5, C6. And so when you bring it to the surface, you're actually producing a lot of gas and compared to the oil. Okay, there's quite a lot of gas produced, so it's quite volatile, which means it's easy to vaporize. Okay, that would be your volatile oil. And then you can actually have a case where a near critical oil, where we're very close to the critical point. So it's not terribly clear: is this an oil field? Is it a gas field? Now, technically, which side is that critical point? Is it to the left or the right? Okay, and we need to determine that. But it is actually near critical. It behaves like a critical mixture. It's not obviously an oil field. It's not obviously a gas field. It produces a lot of liquid and a lot of gas as well. Okay, so that's your combination. Okay, so those are the phase diagrams. Okay, these are quite simple phase diagrams to describe oil and gas mixtures, and they tell you the different types of field and the different ways of describing them. I'll finish with one last thing, which is again sometimes can be a bit confusing. So sometimes you hear, and I've drawn it in black, people talk about a black oil or black oil field. That seems a bit strange because oil is a black color. Crude oil in general is a black color, and the reason for that is lots of branched alkanes that absorb. Said that before. Okay, so that's what a black oil is. When you look at more lighter mixtures, actually, that the hydrocarbon become colorless, right? Petrol, for instance, which is the lighter fractions, is colorless, or sort of yellowy or orangey color. Okay, however, the description of something as a black oil is not, in fact, referring to its color. It's another thing where you think it's referring to its color, but actually it has a technical reason. And the technical reason is actually how we describe oil and gas fields. So, in principle, a hydrocarbon accumulation is a mixture of hundreds of different chemical compounds. And how we might describe them thermodynamically with an equation of state, if we want to put an equation to this phase behavior, is by understanding the behavior of these hundreds of molecules and their interaction between them. But what we normally do is we simplify the description. And sometimes just saying it is a bit confusing because you haven't really thought about it. But how are we going to describe it from now on, right, when we're going to put some equations down, is we're going to assume that, in fact, your hydrocarbon mixture has basically just two components, an oil and a gas. Let's get rid of that. Okay. So you have an oil and a gas. Okay. And the gas can dissolve in the oil. Okay. So we can have the gas dissolves in the oil. Okay. So we have different amounts of gas that can be in the oil. So what we do is we describe our hydrocarbon mixture as a liquid phase, that's oil, and that oil will have properties that will be a function of temperature. And then as a function of temperature and pressure, there will be a gas, and the gas is assumed to have constant composition, and a certain amount of gas can dissolve in the oil. And that model is called a black oil model. It essentially says there are two components. There's an oil, a liquid, that is what you have at the surface, a gas, which is what you also have at the surface, and what you have in the subsurface is just different amounts of gas dissolved. You might say, well, yeah, what's wrong with that? Well, how could it be different? Well, the reason why it'd be different, clearly, if we're near the critical point here, so if we're looking at a gas condensate near critical oil or volatile oil, that doesn't work because we know near the critical point, the gas and oil are very similar compositions. So actually gas has a composition very similar to the oil. When I bring it to the surface a long way from the critical point, the gas actually has a different composition. It tends to be actually lighter, right? More gas-like, right? So when we talk about a gas black oil field, which is the thermodynamic description that we apply to the vast majority of hydrocarbons, what we're doing is we're simplifying thermodynamic description, and that's what it means. So in fact, black oil is a technical description, not a description of the color. Okay, so I think I've said enough for this video. I will be continuing a description of phase behavior later in a subsequent video, but I think for now this is simply introducing those phase diagrams. So I will finish here. Thank you. Thank you.
Okay, let's continue. 5.7 Chops or not? The ingress of sand into an oil or gas well during production increases the flow rate of formation fluid, oil, water, gas by reducing impediments to flow through the pore through of the medium that may be caused by near variable blockage and by the concomitant formation and growth of a high permeability zone around the well. Furthermore, production technologies based on sand ingress eliminate the sand exclusion method, such as sand screens, gravel packers, and filters that invariably impair fluid productions rates and are costly to install and maintain. During evaluation of potassium-heavy oil operations in unconsolidated and poorly consolidated sandstones, sand influx techniques should be evaluated. This sand influx can be minimal or it can be massive. and the amount of sand influx depends on the well design, the completion approach, reservoir characters, and production practices. The possibility of producing larger quantities of oil along with large amount of sand arises only in the case of heavy oil development. In generally cohesive unconsolidated sets, thus the potential for increased production, whereas the increased cost and risk associated with sand influx must be evaluated economically. The major elements of this assessment are where the reservoir produces sand or not, what is the financial benefit of crops in terms of increased production rates, what is the additional financial benefits of not having to install and maintain sand exclusion technologies such as screens and gravel packers. What are the costs associated with the need for sand management throughout the life of the project? What is the cost of the increased operational and environmental risk associated with sand ingress? Are there substantial additional costs related to personnel training and implementation of the asset management approach in the asset structure? The answer to these questions can in many cases be quantified, but the only realistic cost figures available at present are from Canadian heavy oil industry. This industry has 15 years experience with TROPS method and has developed a regional infrastructure to handle sand and heavy oil. In the Canadian HOB, the only economic variable non-thermal approach that has been widely used in the more viscous oils is to encourage sand influx. Years of experience have shown that if there is no sand influx, non-thermal heavy oil above 1000 cp production rates are not economical, with very few exceptions. Also, disappointment with production rates from long horizontal wear is high viscosity oils above 2000 cp has restricted this approach usually to reservoirs with less viscous crude oil, less 1000 cp. The case history present in this chapter are only a small number of the excellent case histories that could be developed at reasonable cost. In many cases, the decision in implement TROPS method is not easily made because there is insufficient information or experience in an area to allow an empirical prediction of the increase oil rate with time. The previous section outlined the complex involved in mathematical modeling. Although great progress is being made, simulations to predict oil rate, period, or for that matter, simulations to help decide whether choice is viable in the first place are not yet in a stage of development where they can be used without substantial field-specific calibration. In such cases, where a reservoir looks interesting and has passed a preliminary set of screen study of relevant analogies and implementations of a pilot project are suggested as the best design approaches. The Canadian experience in heavy oil development, including the rapid technological advance in areas other than crops, constitutes a resource that the world oil industry can use to guide planning and to reduce unnecessary cost or prolonged investments in technologies that have already been shown to be unsuccessful or problem in Canada. Nevertheless, reservoir conditions in other areas must be carefully evaluated in this context. Yeah, this is the figure for this part. The 5.1 is the Rusland field production history, 1982 to 1988. We can see from 1982 to 1994, they used just simple beam pumps to produce the oil, and the sand is little produced. From 1994, they chose the crops to increase the production, and we can see from they use the crops the production have a sharp increase for the following years. This figure is 5.2 production history for Rusland horizontal wear. We can see in this picture is for the horizontal wear, and we can see for the first year is the production is the most of the life of the horizontal wear, and the life of horizontal wear just remain more or less 4 years, and the oil rate decrease quickly from the first year, and in the last years it remains. The production is stable. However, in many Canadian fields with less than 1,000 meters horizontal wear are successful, 300 to 600 barrels per day. Nevertheless, the daily rates tend to drop by 25 to 40% per year, giving short wear life. The figure 5.3 chops wear, 5.4 Rusland field. This wear is the same as the whole field of Rusland. After start crops, the oil rate is increased quickly. 5.4 crops wears 13 loose land field. This wear is not good after start chops. Figure 5.5 loose land vertical chops wear 3-7. We can see this vertical wear have a better performance than the last one. When they start the chops and the oil rate increase quickly and remain maybe 5 or 6 years. Figure 5.6 Cumulative liquid production always. Figure 5.7 average monthly oil rate versus average monthly water rate. Figure 5.8 plot of water oil residue versus oil production rate. The anomalous cases suggest that water flooding may be successful in some chops reservoirs, and that high water rates are not necessary. Figure 5.9 Production from a vertical chops were in Limburg field, Albert. In this field, show us a good result for chops. 5.10 Production from horizontal well in Limburg field. The horizontal well is the same as the Loufland field. First 3 years, the oil rate decreased quickly, but the initial oil rate is good, and the horizontal well lasts just 4 or 5 years. Figure 5.11 Water and oil cumulative production comparison. We can see vertical well has a good result than horizontal wells. The total production is more than horizontal well. 5.12 Water and oil communication production comparison. Clover Lake field. This field shows us the same result. The total oil production vertical well is better than horizontal well. 5.13 Water and oil cumulative production comparison characters lake field. It shows us good. Oh no. In this field, the horizontal well, the total production, oil production, is better than vertical well. Figure 5.14 Changes of processes as a function of porosity. Figure 5.15 Simple functions selected to emulate in-suit permeability distributions. Different permeability distribution models can be used depending on one's view of physical nature of the zones around the well.